Ladies and gentlemen, welcome back to this afternoon's session of today's HAPP conference. My name is Harvey Brown. I am an emeritus professor of philosophy of physics here at the University of Oxford. I have attended with great profit many, if not most, of the conferences organized by HAPP over its illustrious 10-year span. And so it gives me enormous pleasure to have the privilege of chairing this session. And without further ado, I would like to call on Professor Nikk Effingham from the University of Birmingham to speak to us this afternoon about tachyons.
Thank you. So I'm Professor Nikk Effingham. I'm the head of Department of Philosophy at the University of Birmingham, and I'm delighted to be here today to talk to you about my research speciality, which is the philosophy of time travel. And in this talk, I'm going to just talk about three things. I'm going to talk about something you probably know about, which is the grandfather paradox. And if you don't know about it, don't worry, I'll go through it as we get to it. And then I'm going to talk about how weird probability and chance works when we start considering time travel. And then I'm going to end by discussing what kinds of upshots these fanciful tales, as one philosopher once said to me, these fairy tales, might actually bear upon contemporary physics and the world as we know it. So I'm going to do three things. So let's start with the grandfather paradox. You probably know about the grandfather paradox. You've probably seen it in some form in television or film of some variety. If I had a time machine, isn't there a problem? Isn't there a problem? Couldn't I use that to go back in time and kill my grandfather before he met my grandmother? And if I did that, then I wouldn't be born. And if I wasn't born, how would I get into my time machine to go back and kill him? This has been around almost as long as stories about time travel themselves, first appearing in the works of René Barjavel, a French author who wrote about time travel. And it's become the focus of a lot of theoretical discussions, both within physics and also, most importantly, within philosophy. There are, jumping ahead, there are, roughly speaking, three solutions to the grandfather paradox. You are faced by three choices. The first choice is you might think that time travel is impossible. The other two choices are that, in fact, you can time travel. One choice is that you can time travel and you can change the past. So you can time travel and you can go back in time and you can kill your grandfather. And the other choice is that whilst you can travel back in time, you'll be unable to kill your grandfather. And it's this last one that I'm going to spend most of this lecture focusing on, most of this talk talking about. But I'll very briefly discuss the first two. So the first one is that time travel is impossible. Sometimes we use thought experiments to tell us about the world. We've just had Maxwell's demon. That was a form of thought experiment. There's also thought experiments in some other places, such as those that Galileo used to demonstrate that objects will fall at the same rate, no matter their mass. So you might think that this grandfather paradox is in fact a thought experiment that demonstrates that time travel is impossible. It's a dead giveaway that we'll never be able to make a time machine and that we shouldn't spend our time thinking about physical theories that might allow for it. Me, I'm a little bit more deferential. I don't think the thought experiment necessarily proves that. I'm happy to leave open the door to think that actually, if we want to find out whether time travel is possible or not, I have to do more than sit in my armchair and think about Star Trek. I actually have to defer to the physicists, and they have to tell me whether time travel is possible or not. So I'd rather think that the grandfather paradox doesn't prove by itself that time travel is impossible. So I'm more interested in the other options. What would happen if the other options were true? The second one, it's a little bit fanciful. The idea that you can go back in time and change the past. It seems to be contradictory. If I shoot my grandfather, how is it that my grandfather was both alive in 1930 to meet my grandmother, and now he is dead in 1930? How can he be alive and dead? It's at this stage where we hear these stories about other universes. When you go back in time, you arrive at a different timeline, a different universe. Certainly you'll have seen this in fiction if you're a Star Trek fan or a Doctor Who fan or a Futurama fan. Every sort of fictional story about time travel at least flirts with this idea of multiple universes and the idea that when you time travel, you don't end back in your past. When you time travel, you end up in the past of some other universe, some other kind of reality. And it's not just, I don't want to say that it's merely fanciful, because there are serious physicists who believe this. People like David Deutsch, Michael Lockwood, they've argued that properly interpreted quantum physics kind of indicates that this is what would go on if time travel occurred. There's a lot to be said. You could probably do a whole lecture, you could do a whole series of lectures on this kind of theory in and of itself. But I'm not really going to talk about it today. I'm interested in this final option. The final option is that time travel is possible, but no universes are needed. Reality doesn't need to provide you with an extra universe for you to end up in when you use your time machine. When you time travel back, you can time travel back. You can take a rifle back into the past. You can point it at your grandfather, but you won't kill him. You won't kill him. You will fail. Something will stop you. Something will get in your way. Something will interrupt your attempted assassination. This, again, appears in many science fiction films. It's also one of the more popular theories of time travel in philosophy, promulgated by a philosopher called David Lewis, most famously, but not only. And they believe that when you go back in time, something will stop you from changing the past if you try and change the past. That starts to raise some interesting questions, because if something stops you, you might want to know, well, what explains something stopping you? If you send 1,000 people into the past, if there's a society of auto-infanticidal assassins, each of who goes into the past looking to kill their grandfather, according to this view, each and every single one of them will fail. They'll all have a heart attack on the way there, or the gun will misfire, or they'll all change their minds, or something. Something will stop each and every one of them. And that seems to cry out for some kind of explanation. What would explain our inability to change the past? What explains the fact that I can't shoot my own grandfather with a rifle? Well, that's definitely philosophy. Philosophy deals with the nature of explanation. That's one of the things that you do in things like philosophy of science. When we look at explanation, there's different types of explanation. So, for instance, sometimes there's agental explanations. We explain things in terms of agents. Why is that cup of tea there? Say my parents to me as a child, and I go, oh, I've left it there. The explanation is in terms of an agent, me, and what I do. So some explanations in terms of people, of subjects like you and I. And, you know, you might have an agental explanation for why I can't kill my grandfather. You might imagine that the explanation for why I can't go back and kill him is that there's some kind of time agency, a bunch of people who are minded to put themselves to the task of preventing me every time I try and change the past. But surely this is the work of fiction, not reality. We don't actually think there's a time agency out there. If I had an actual wormhole into the past, I don't seriously suspect that some time cops would turn up and stop me from killing him. The next explanation would be a natural explanation. We explain things in terms of the laws of nature, the laws of physics. And again, whilst conceivably I might think a law of nature explains why I'm unable to kill my grandfather, it still strikes me as a fairly strange law of nature. It still seems to be slightly odd. Why is it that I can kill that person over there right now with my sniper rifle, but I'm unable to have that same ability when I'm back in the 1930s, pointing at someone who's substantially qualitatively the same, my grandfather? How do the laws of nature know that I've kind of come back from the future? But there's a third type of explanation, and it's the one that I'm going to focus on in this lecture. It's a logical explanation. Sometimes we explain things merely by the laws of logic. For instance, if I gave you 10 squares and asked you to arrange those squares into a larger square, you would be unable to do it. You can arrange 9 squares into a larger square, but you can't arrange 10 squares into a larger square. How would that work? But the explanation for that isn't, say, some law of nature. It's not as if the laws of magnetism are kind of pushing that 10th square in such a way that you can't make the biggest square. It's not as if there's a law of physics that's getting in my way. What explains your inability to make a larger square out of 10 squares is it's a law of logic, it's a logical fact. It's just logically impossible to bring about the contradiction of a square made of 10 smaller squares. That's a logically impossible thing. That explains why you can't do it. So it is, I think, in the grandfather paradox. When you go back in time, when I go back in time to shoot my grandfather, let's call him Pappy. When I go back in time to shoot Pappy with my rifle, I will fail. I will fail to succeed. But the explanation for this isn't that someone is stopping me. Nor is the explanation for this that we need some special law of nature. The explanation is just that you can't do the impossible. You can't make it the case that Pappy is both dead and alive in 1930. This, as I say, is quite a popular theory of time travel within philosophy. And I'm quite interested in the follow-up question. If that's the correct theory of time travel, how would probability function? How would chance work? Even if it's possible to go back in time and shoot my own, even if it's possible to go back in time with the rifle and fail to kill my own grandfather, how likely is that? What are the likelihoods here? And it turns out, from my research, I'm also going to plug a book. Turns out, after I did the research on my book, that probability works very oddly in time travel cases. That if you've got this theory of time travel, unsurprisingly, chance starts to work quite strangely, quite bizarrely. To get your head around this, let's simplify things. Just consider a simplified situation where you're fairly certain the only thing that could stop me killing my grandfather is either my gun misfiring or me having a heart attack, and that stops me. So I'm thinking of heading into the back, I'm thinking of heading off to kill someone, and these are the only two things that might get in the way, that might cause me to fail. So here I am in the present day with my gun, and my gun is well oiled. I keep it in good condition. It's new, I've just bought it from the shop. The chance of a misfire is quite low. And I'm a healthy 45-year-old man. I'm unlikely to have a heart attack. I've just seen the doctor. I feel in rude health. If I picked up that gun, please don't do this. If I picked up that gun and went outside and just found a random person, please don't do this, and tried to shoot that person, please don't say that I made you do it. If you did that, if I did that, what would happen? Well, because the chance of misfire is low, and because the chance of me having a heart attack is low, and they're the only two things that could stop me, I guess the chance of me killing that person would be quite high. That seems to be fairly standard. That's why you should probably prevent people having high-powered rifles, because if they took a fancy to it, they could quite likely kill people, because the chance of having a heart attack and misfire is quite low. But if you've got this theory of time travel, if you endorse this kind of philosophically popular theory of time travel, it works differently when I do it in the past. So if suddenly it's not the contemporary day, if now we consider that it's 1930, and I've gone back in time and found my grandfather, and now I'm pointing a rifle at him, what are the chances? Well, we know that my chance of success is zero. We know that it's impossible for me to succeed. I cannot possibly do this thing. But if we have assumed that the only two ways, and it is just an assumption, but it's just a simplifying assumption, if we've assumed that the only two ways for me to fail are for my gun to misfire or for me to have a heart attack, well then I guess the probabilities of those things has to skyrocket. Now it turns out, if I'm back in 1930, the chance of a misfire is super high. Now it turns out that my chance of a heart attack is also really high. Time travel is dangerous for my health. If I set my mind to killing my grandfather, this is a deadly thing that I'm doing. This is bad for me. He's going to get away scot-free, and we know he's going to be fine. Me, on the other hand, not so certain. Not so certain. Okay, so that's a simple example case that shows that when you consider a time travel situation, this theory of time travel means that chance plays out differently. Now, we've assumed two things in this example case. One is that I've gone back in time. It turns out that you don't even need that. So imagine that it's the modern day, and I'm sat there looking at my TARDIS, contemplating going back in time to kill my grandfather. What's true in that situation? Well, it's exactly the same. There's no reason that the heart attack that gets me has to take place in 1930. All we know is that something stops me, such as a heart attack. And there's no reason to think that that heart attack won't get me now as I contemplate looking at the TARDIS. The more dead set I am on getting in that TARDIS with my gun and going back to kill my grandfather, right there and then, the chance of me dying is increasing. Now, that might sound strange, because you might go, well, how's that meant to work? How do the laws of physics know that I'm about to do that? How do they know what my plan is? But that, of course, is where this idea of logical explanation comes back. If I'm sat there contemplating going back in time and then keel over, you would be right to say that would be explained by my intention to go and kill my grandfather. But the explanation would not be one of the laws of nature. It would be one of logic. It would be logically explained by me going back. Logic doesn't need some special mediative force to prevent me getting into the TARDIS. It is like the squares, just impossible to do. So similarly, the explanation for the chance of my heart attack going up would just be logical. So these things might go on, these weird things to do with chance might go on even if you haven't traveled back in time. Just if you're in the vicinity of traveling back in time. And that applies even in other cases. So imagine it's now, and I've got no TARDIS. But if I don't die, then in 10 years' time, I will build a TARDIS and go back in time and try and kill my grandfather. Same reasoning applies. Even in that situation, when unwittingly I haven't even thought of killing my own grandfather yet, because I don't know how to build a time machine. Even in that case, I suggest that the chance of a heart attack is still quite high. The other thing that's being suppressed in this example about time travel is that it makes it sound like these weird chances only occur when you go and try and do something serious, like killing your own grandfather. Something quite major, something that would make a big difference to the timeline, as Captain Kirk or whoever would say. But in reality, I think any kind of time travel will fall in the same boat. Why is that? Well, imagine I go back in time, and I'm not going to kill my own grandfather, but I'm just going to step out in 1930 into the Gobi Desert. And I have a quick peek, no one around for miles, I have a quick peek, and I just go, I'm going to go back to the future. You might think that there's no contradiction in that. You might think that that hasn't changed the past. But that's not true. Because as I step out into the Gobi Desert, my mass casts out gravity waves at the speed of light that subtly, just minutely, alter the position of atoms across the entire universe, at least within my future light cone. Whilst it might not be the case that me going back in time to the Gobi Desert will result in Hitler winning World War II, it will mean that he loses World War II with his particles in a slightly different position than they previously were. And that's just as contradictory as my grandfather being both dead and alive in 1930. The universe doesn't care about my grandfather per se. The universe cares about all contradictions, even if the contradiction is that this tiny little atom here is both in this location and in this location, just because I stepped out in the Gobi Desert. So no kind of time travel can take place. Any kind of time travel is going to raise the chances of me dying if I try and do it. If I have a TARDIS and I'm thinking of going back to do any kind of time travel, this is going to increase the chances of me dying. This is going to play oddly with the way the probability is working. Even the quickest of quarks or the smallest of superstrings would be unable to pass into the past on this view. It would be possible, but very, 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 very unlikely. It would be possible for it to do it, but it would have to do it in such a way that it perturbed reality in just the right way so everything stayed the same. That seems exceedingly unlikely. Okay, so there's some fanciful tales of TARDISes and going back in time to kill our grandfathers and stepping out into the Gobi Desert and so on and so forth. What has this got to do with the world at large? What has this got to do with the world as we deal with it? What might it tell us about things that we're doing now? Well, one lesson is that you shouldn't spend your time trying to build a time machine. That's bad for your health. Right. Obviously, that's easily done. Right. All you have to do is decide not to do that. You can go, oh, I'm thinking of building a TARDIS. No, no. I listened to that Nikk Effingham once. I'm going to go and watch Strictly Come Dancing. It's easily done. It does, however, also mean these things don't matter about intention. Even if I'm thinking to go back in time in a way that would accidentally kill my grandfather, that would be a problem. Unintentionally changing the past is a problem. And if all time travel almost certainly leads to changing the past in some way, then even unintentionally building any kind of time machine is a bad idea. Elsewhere, I've kind of made a case that this might be, I've got to be very careful. I don't want to make it sound like I'm trying to ban running particle accelerators. That's not where I'm going with this. But you might wonder whether when you're activating a particle accelerator, you should definitely make sure that there's going to be no time travel whatsoever, even at the subatomic scale. And at least sometimes people have suggested that this might go on. I'd suggest that you should at least, listen to these people in the same way that when the military worried that using nuclear weapons might accidentally ignite all of the oxygen in the Earth's atmosphere, it was worthwhile making sure that that probably wasn't going to happen. I would stick this on the table of things we should do. If you're going to do an experiment, put the effort in to make sure that you're not actually going to create any type of wormhole, which many scientists, I'm sure, would tell me is not one of their great worries. Nevertheless, given it might kill you and those around you, I'd spend at least a bit of time bearing it in mind. But today I'm going to talk about tachyons. These kinds of questions about probability seem to bear on our understanding in physics, particle physics, of tachyons. So what's a tachyon? So, a tachyon is a particle that goes faster than the speed of light. And as we know, if you go faster than the speed of light, you go back in time. You might think this is not a problem because you might think, if I know anything, I know that Einstein told me that nothing can go faster than the speed of light. But if you believe that, you would be wrong. What Einstein in fact says is that nothing can accelerate past the speed of light. If you start off going slower, you can't accelerate past the light barrier. Equally, if you're a photon and you start at the speed of light, you're always going to stay at the speed of light. But equally, maybe if you start off past the speed of light, if you're an object that has always traveled faster than the speed of light, if you're a tachyon, well then in fact that's permissible according to at least some interpretations of Einstein's of the theory of relativity. If there were tachyons, they would be pretty weird things. So, for instance, because they can never slow below the speed of light, that means that when they approach a gravitational source, like a black hole, rather than accelerating towards it, they'll kind of slow down. And as they leave a gravitational source, rather than sort of slowing down, they'll speed up. They go in reverse. They've kind of got negative mass. They would be odd things. They would be odd, strange things. But if they did exist, we might be able to manipulate them. And we might be able to then use them to communicate with the past. They might also play a role in our physical theories. For instance, it has been suggested by some people that protons might, like a radioactive particle, they might decay. They might decay. But when they decay, they'll sort of give a little kick as they decay and emit a particle. So your proton will go this way, and some other particle will go that way. However, said certain physicists, There's a law of physics, the conservation of baryonic number, that says that the number of protons that exist has to remain constant. So when the proton decays, it actually doesn't go anywhere. So it's a little bit unlike radioactive decay. You'll be left with a proton. But that means that when proton decay occurs and the proton goes this way, well, hasn't energy just appeared spontaneously out of nowhere? The proton goes this way, another particle goes that way. And haven't you just spontaneously created mass? This particle that has been shed in the decay process is generated mass during the decay process. Aha, they said. It would work if it was a tachyon. Why would it work if it was a tachyon? Because whilst the proton gains some energy going this way, the tachyon has negative mass, so negative energy, and it heads off this way. So it kind of balances out. You can create energy if you create something with negative energy at the same time, they reasoned. So maybe in the process of proton decay, tachyons would be produced, counterbalancing the energy from the proton. So we've looked for them. We've looked for tachyons. We've looked for tachyons. And we have never seen them. We have never found a tachyon. There's no evidence of any tachyon. Well, there's not compelling evidence of tachyons. There's very defeasible evidence of tachyons. Even the person who came up with the most plausible citing of a tachyon or detection of a tachyon promptly explained later why he thought that was misguided. So we've not found them. They don't appear to be out there. And you might reasonably draw from this that theories that say that tachyons exist, theories that involve tachyons, your theory of proton decay that works in this sort of way, they must be false. They're not the correct laws of physics. You might think that it means that theories that involve tachyons don't turn out to be true. But now we can bring it home. Now we can bring it home. We've got this theory. We've got this theory of how probability works in time travel cases. And we've got these tachyons. And if tachyons existed, you would have a form of time machine. They would be going back in time. You would be able to manipulate them to talk with people in the past. You know, you'd be able to tap out Morse code messages in tachyons. Beep, 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 beep. Can you kill my grandfather? Beep, beep, beep. You'd be able to change the past just as much as stepping into a TARDIS. So we should take the lesson that we learned about me trying to kill my grandfather, and that lesson was that any kind of time travel will result probably in changing the past, and any sort of time travel like that is probably, almost certainly, going to be thwarted by random chance. We're going to take that lesson and we're going to deploy it here. So you're sat there looking at your proton, checking to see whether it decays. Obviously, in reality, they had a bubble chamber full of lots of protons and hoped that one of them would decay at some point. You have your proton and you're waiting for it to decay. And you have predicted that there's a whatever chance, a 20% chance, a 30% chance that it's going to decay. And spit out the tachyon going one way and it goes the other way. But whilst it might turn out that it's physically possible, whilst it might turn out that looking at that situation on its own, there's every reason in the world to think that this is probably going to happen, that's only the same as focusing in on the situation where I'm pointing my perfectly well-oiled gun at my grandfather in 1930 and you concluding that I'm very likely going to kill that guy, and then me dropping dead moments later. Once we take into account the fact that this is a time travel situation, you should actually think that whilst it's physically possible, the chance of it is low, that it's basically nil. It's almost certainly not going to happen. In the same way that I'm almost certainly not going to be able to go back in time to kill my own grandfather, or go back in time at all. I definitely can't kill my own grandfather, but can I even step foot into the Gobi Desert? Probably not. Probably not. So the chance of it becomes really low. And what explains the chance of it coming low? It's not physics. It's not a physical explanation. It's a logical explanation. If it spat out a tachyon, you'd probably have a contradiction. So even though reality is kind of gagging to produce tachyons left, right, and center, these worries about time travel and contradictions kind of hold back that process. So what's the upshot of that? Well, the upshot of that is that even though we've gone looking for tachyons, and we've not seen any of them, that is actually not a reason to think that the theories saying that there are tachyons are in fact false. And that's my talk on how the philosophy of time travel bears on tachyons.
Thanks very much. Questions? Comments? Yes.
Can I ask in two parts?
Yes.
Do I need to use it or?
I think it's
Okay. So first of all, I wanted to ask, how does this work with Rocco's basilisk? Because you mentioned the fact that, oh, you don't even need to think about making a time machine. But suppose I work in technology, and what then prevents me from saying, oh, whatever I produce on my workplace will eventually lead to the time machine, which eventually will lead to that kind of thing. So how, if I take your argument ad absurdum, so how does it work? Can you explain that real quick?
Oh, so according to me, well, don't do that. That's actually raising your chance of dying. Or is it? Is it? Maybe it's not, because when you form the intention, well, you might just be on the road for hiding anyway. If there's not going to be any time travel from your discovery, if you're not actually doing research in technology that will lead to a time machine, you're safe as houses. You're just deluding yourself that this is going to lead to time travel. But if it was true, then you would in fact be risking yourself in some sort of ways. Obviously, I'm not suggesting that most definitely you would keel over, because there's all kinds of things, all kinds of events between now and the creation of the time machine. Say 10,000 years later, they take your research and think about using a time machine. Well, there's 10,000 years of events that might get in the way. But your intention might, for instance, be raising the chance of a global nuclear war in the year 4000 that wipes us all out, which is what explains why we don't make the time machine in the year 10,000. So it is dangerous. It is dangerous. But you might take from this the fact that nothing dangerous has happened to you, that you are, in fact, not going to succeed.
And the quickly second part, how does it, so suppose I step out in the Gobi Desert with the time machine, how does it interact, like how does it interact with the concept of it had to happen? So for example, the events had to go this way, where I develop time machine and then I go back to Gobi Desert and then I step out, do some minor perturbation, and that actually falls onto itself to make that universe. Why, didn't you mention that, but the universe from the past has to remain constant?
So that's a fair question, and I'll do that in a two-part question. So part one of my answer is, that's quite difficult. What you need to go and do is the chapter 9 of this book, which goes through it step by step and slowly. The rough idea is, if you imagine the kinds of situations that might come about, the vast majority of situations that might come about are situations where, if there's time travel, there'll be a contradiction. And whilst there absolutely is a physically possible situation where I go back in time to the Gobi Desert, pop my head out, and then go back to the future, it's one of so few situations that's why you should conclude that the probability of it is low. That's kind of the Cliff Notes version. The actual argument is more sophisticated and doesn't run into as many flaws that one might have with that process of reasoning. But yeah.
This is in a way variation of the first question of the first questioner. Suppose the time travel is possible and we go back 10 years or whatever and make a perturbation. Is it not that we really know the impacts through the game of life, where after certain generations, it will be more or less the same, on average the same, but there are only many different versions of the outcomes or its generation?
So certainly we know that we're in some logically possible situation that might be generated by some kind of algorithm like the game of life. The worry is, are you more likely to be in the logically possible logically possible situation where you go back in time, or are you more likely to be in one of the very logically possible situations where you die before you get to do it? And so my claim is that whilst the types where you go back in time are possible, they're nevertheless very, very unlikely, because having the setup whereby the past leads to exactly the sort of arrangement of particles that lead to the past having exactly that arrangement of particles, that's such an unlikely setup for you to end up being in. Obviously, if you assume that you're in that setup, well, the chance is 100%. But that's true of everything. What's the chance of me rolling 6 27 times? Very low. What's the time of me rolling a 6 27 times if I assume I've rolled it 26 times? Oh, it's certainly not looking so bad now. So be careful not to build into the situation your assumption that you have gone back in time already.
We have time for 2 more questions. There was one up here, and then there's one down here.
Thank you very much. I have 2 questions. They're completely orthogonal, but both interesting for me. The first one relates to the fact that we use a logical reasoning to justify if something is possible or not, but there are famously problems with logic itself. Logic is incomplete according to Gödel's theorems. So what would that translate into this framework? And the second one, it's related to the quantum eraser experiment, and how does this figure out in this framework? Because is interpretation wrong?
So what was the last bit? Quantum erasure, did you say?
The quantum eraser experiment.
Okay. I won't lie, I'm a poor, impoverished philosopher who, when it comes to physics, so I'm not sure if I'm familiar with that. I can answer the first question, I believe. So I'll try and answer the first question. Yep. You might try and draw that there's some kind of funky logic going on that might allow for these contradictory situations to take place. I mean, I don't want to rule that out from being possible. There are what are called paraconsistent logics, dialethic logics, that allow for contradictory states of affairs. I actually think that if you endorse one of those theories, you end up with something very similar to the situation where you can go back in time and you can change the past, but you end up with many, many different universes like this. So I think you end up with something functionally identical to this. In fact, I think if that was the explanation to the grandfather paradox, you would be unable to tell whether what was really going on was that you live in multiple realities, or you live in a reality which is kind of copacetic with contradictions. I don't think there'd be a way to tell between them, ultimately. Yeah.
Question there.
Professor Ford taught us that probability is subjective. In your example with the misfiring and the heart attack, the probability outcome for one of those parts, one of those components, is obviously the machine part, so the gun. The other part is the human, the heart attack. So how are we supposed to combine the machine and the human subjectivity? Because it seems to me that there's some type of quantum entanglement inherent in that.
I guess ultimately I'm on the side of people who think that probability is more objective than subjective. So there's an objective probability out there which you are trying to aim at with your probability beliefs. And in time travel cases, it turns out that the objective probability that you're aiming for isn't the objective chance that the universe thinks it is. You kind of know better than the universe, because you know that a logical contradiction isn't going to come about. The universe is kind of blind to that because its laws don't seem to rule that out, at least in a time travel case. So I think that would be how I would move around that. First of all, endorse a more objective view of chance, and then have this view that there's kinds of 2 tiers of chance going on. There's chance as the universe understands it, and then an updated chance as the universe understands it, conditional on there being no logical contradiction.
Right. Last question. Thank you.
Okay, this is a physics question that needs a philosopher to answer. There are, it happens more often than we want to admit, there are 2 camps that seem to be emergent now within people who think about quantum gravity and time. Ravelli's idea of an emergent, time being an emergent quantity, which is an illusion, and Smolin et al., I'm more biased towards this, thought that it's actually something distinct and absolute, as a philosopher of time, can you give us some guidance of what we should be looking at?
I mean, I could. That's definitely a full lecture afterwards. It would be very difficult for me to cram that into a simple answer. I mean, the philosophical camps, broadly speaking, mirror those camps. And so you'll find people on both sides trying to push their lines. If you ask me my opinion, I'm quite deferential to physics, and I think that would be closer to something probably like Lavalley's account. I think, but I could be wrong. Like, don't quote me on that.
At this point, I'd like you to join me in thanking Professor Effington for his talk.